All right, this week we are going to move to Chapter 11, first two sections, DC circuit analysis, Ohm's law. So a lot of this is, again, building on what we've already learned, more application specific. We're going to look at the first two sections, resistance in series and parallel circuits, and learn how to compute total resistance in the circuit, both series and parallel, and then later the combination of the two types of circuits. Ohm's law expresses the relationship between voltage, current, and resistance in an electrical circuit. And as we can see, depending on which configuration of Ohm's law we use, depending on what we're solving for, current, resistance, or voltage, we have values that are either directly proportional or inversely proportional. In the first one, we see that current and voltage are proportional directly, where resistance is inversely proportional. The configurations of a series circuit depends on each of the resistors, in this case, being tied together end to end and forming one path for the current. So in doing this, the total resistance in the circuit, depending on how many resistors we've got, will be merely the summation of all of the resistors added together. We have introduced conductance in the past, and we use conductance sometimes in our analysis and our calculations because in some cases it's easier to solve for the relationships if we use conductance. In this case, in a parallel circuit, notice how the configuration of the circuit has changed. Instead of them being tied end to end, they're tied together in what we call nodes. So if you look at the diagram at the bottom, R1 and R2 really form a node top and bottom. Okay, the relationship then of conductance in a parallel circuit is that summation. So when we look at the ability to add their values together, if we calculate in a parallel circuit a conductance, the math becomes a lot easier. Otherwise, as you can see below, we end up with an inverse relationship for conductance. For resistors connected in parallel, then, the total conductance equals the sum of the individual conductances. So in this case, we have three resistors connected in parallel, 1, 2, and 3. If we can convert the values of the resistance, R1, R2, and R3, into a conductance, we can merely add those values together. So since we were given resistance instead of conductance, we end up taking the inverse relationships for each of those resistors, and now they become a simple sum of 1.47 milli, 667 micro, and 445 micro Siemens, respectively. So then the last step then is converting it back to a resistance by doing the inverse of the operation we did initially, and we end up with 386 ohms. Rule 11.1 says that to find the total resistance in a series parallel circuit, we determine which resistors are in parallel and reduce that part of the circuit to an equivalent resistance. So in this case, if we look at the diagrams below, we can see stepwise the reduction of each step of the parallel branches into a series branch, and then making a total for each of those steps. Okay, so in the first step, what's in the green box is our first step of combining the two resistances together as conductances, and then adding them in the second step to R1 to give us our total. So if we look at the relationship here, RT, our total, is equal to R1 plus R2. R2 is in parallel with R3. So step 1, step 2, and step 3 as we move across the page. In this case, we end up converting our values into conductances, adding them together, and then converting them back to a resistance as our final step, because we normally deal with resistance and not conductance. Dealing with the conductance value simply makes the math easier sometimes. Okay. In this case, we've got a series parallel relationship that's going to occur. So we've got two series resistors in the first step that we're going to add together, simple sum, and then we end up with two resistors in parallel that we use the conductance relationships to solve for, and then the last step then is converting the resistor back to a resistance value in ohms from our value in Siemens, which is our conductance value.